Hello there, and welcome to Space Historians. Tonight, we'll be drifting through the quiet science of black holes. These remarkable objects exist throughout the universe, holding secrets about gravity, time, and the nature of space itself. Even now, as you listen, light from distant black holes is traveling toward Earth, carrying stories that began millions of years ago. Every breath you take unfolds in a universe where these cosmic mysteries continue their patient work, shaping galaxies and bending time with a stillness that asks nothing of you. Black holes are not what fear imagines them to be. They are natural, elegant, and surprisingly gentle when seen from our comfortable distance. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy and allow your mind to relax. Let the vastness of space become a blanket rather than a burden. Let's begin. A black hole is a place where gravity has become so strong that nothing can escape once it crosses a certain boundary. This boundary is called the event horizon, and it marks the edge of a region where the pull of gravity exceeds even the speed of light. Light itself, the fastest thing in the universe, cannot climb back out once it passes this threshold. The center of a black hole is called a singularity, a point where matter has collapsed into infinite density. All the mass that formed the black hole is compressed into this impossibly small space. Everything that falls past the event horizon eventually reaches this center, where the usual rules of physics begin to blur and fade. The event horizon is not a physical surface you could touch. It is simply the mathematical point where escape becomes impossible. From outside, you could never see anything cross it. Time itself behaves strangely there, stretching and slowing in ways that make the boundary seem frozen. What makes black holes so remarkable is not that they trap light, but that they exist as natural consequences of gravity itself. When enough mass gathers in a small enough space, the fabric of space and time curves so steeply that it folds inward, creating a one-way path toward the center. You might imagine a black hole as a cosmic drain, pulling everything nearby into oblivion. But the reality is far more peaceful. Black holes simply sit in space, exerting gravity just as any massive object does. If the Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now. The planets would not spiral inward. The black hole would not reach out and grab them. Gravity would function precisely as it always has, simply following the same laws that govern every star and planet. The reason we call them black is that they emit no light of their own. All the light that approaches them either bends around them or falls inward, never to return. When you look toward a black hole, you see darkness not because it is actively consuming light, but because light cannot reflect back to your eyes. It is the purest absence, a shadow cast by gravity itself. Yet even in this darkness, there is structure. The space around a black hole hums with energy and motion, matter spiraling inward, light bending into elegant arcs, and time itself becoming something soft and negotiable. Black holes remind us that the universe contains room for both mystery and precision. They are objects we can describe mathematically, yet they guard secrets we may never fully uncover. They are proof that gravity, given enough concentration, can reshape reality itself. Where gravity holds all things gently, the laws of physics take on forms that challenge our everyday intuition. Space curves back on itself. Time slows to a crawl. And yet, through all this strangeness, the mathematics remains consistent, describing these objects with equations that have never failed us. The boundary that light cannot cross becomes a kind of horizon in the truest sense, just as a horizon on Earth marks the limit of what you can see. The event horizon of a black hole marks the limit of what can ever return to the observable universe. Beyond that line, information flows only inward. Causes lead to effects that can never reach back out. It is a one-way membrane woven into the structure of space-time itself, as fundamental as the speed of light or the constant pull of gravity. Understanding what black holes actually are requires letting go of the idea that they are exotic or unnatural. They are simply what happens when gravity is allowed to do what it always does, but with nothing left to resist it. When the forces that keep stars inflated are exhausted, when the particles that maintain structure can no longer push back, gravity completes its work. The result is not an aberration but an endpoint, a natural state that matter can achieve under the right conditions. In this sense, black holes are as ordinary as rocks or rivers, just operating under circumstances so extreme that they reveal aspects of nature we rarely encounter. Let your breathing slow. Most black holes are born from stars. When a massive star, many times heavier than our Sun, exhausts the fuel that keeps it burning, it can no longer support itself against the inward crush of its own gravity. For millions of years, the star has balanced two forces: the outward pressure of nuclear fusion in its core, and the inward pull of gravity trying to collapse everything toward the center. When fusion stops, that balance ends, gravity wins, and the collapse begins. This collapse happens quickly. The core of the star implodes in less than a second, compressing matter to extraordinary densities. Electrons are forced into protons, creating neutrons. If the core is massive enough, even the neutron pressure cannot stop the collapse. The core continues shrinking past the point of any known resistance until it becomes a singularity, an infinitely dense point at the heart of a newborn black hole. The outer layers of the star may explode outward in a supernova, but the core has already transformed into something entirely new. Not every star becomes a black hole. Only the most massive stars, those born with at least 20 to 25 times the mass of the Sun, have the gravitational strength to create one. Smaller stars end their lives differently, becoming white dwarfs or neutron stars. But when conditions are right, when a star is massive enough and its core collapses completely, a black hole is the inevitable result. It is not a failure or an ending, but a transformation. The matter that once shone as starlight now exists in a form so dense that its gravity reshapes space itself. The singularity at the center is surrounded by the event horizon, which forms at a specific distance determined by the mass involved. For a black hole with 10 times the mass of the Sun, the event horizon would have a radius of about 30 kilometers. Everything within that sphere is beyond the reach of the outside universe. From the moment of formation, the black hole exists as a permanent feature of space, invisible but present, holding the compressed memory of the star that created it. These stellar mass black holes are the most common type in the universe. They drift through galaxies, often alone, sometimes paired with companion stars that orbit them. When a black hole has a companion, gas from that star can be pulled toward the black hole, creating brilliant displays of light before it vanishes past the event horizon. But many black holes have no companions. They travel through space in silence, detectable only by their gravitational influence on nearby objects. The process of stellar collapse is one of the universe's most dramatic transformations, yet it happens in silence. There is no sound in space to carry the thunderous implosion. The star's core compresses, the event horizon forms, and a new black hole takes its place among the quiet architecture of the galaxy. Born from stars that completed their journey, these objects represent both culmination and continuation. The star's life ends, but its mass persists, now concentrated into a point that will exist for timescales far exceeding the star's original lifespan. In a way, black holes are the universe's way of preserving the legacy of massive stars. Every element heavier than hydrogen that the star created through fusion remains, locked within the event horizon. The carbon, oxygen, iron, and countless other atoms that once made up the star's body are still there, contributing to the black hole's mass. Nothing is destroyed in the formation of a black hole. It is merely reorganized into a denser, simpler form. The birth of a black hole also sends ripples through space. The collapse itself can generate gravitational waves, and if the outer layers explode as a supernova, the blast can enrich the surrounding interstellar medium with heavy elements. These elements will eventually become part of new stars, new planets, perhaps even new life. The death that creates a black hole also seeds the cosmos with the raw materials for future creation. It is a cycle as old as the universe itself, playing out in every galaxy across billions of years. Understanding this process helps remove some of the mystery and fear that black holes often inspire. They are not supernatural or malevolent. They are simply the natural outcome when certain stars reach the end of their fuel supply. The same physics that governs every other stellar process also governs this one. Black holes follow the rules. They are part of the pattern. The event horizon is the defining feature of every black hole. It is the boundary that separates the inside from the outside, the point of no return beyond which nothing can escape. To understand it, you must first understand escape velocity, the speed required for an object to break free from a gravitational pull. On Earth, escape velocity is about 11 kilometers per second. For the Sun, it is much higher. The more massive an object and the closer you are to it, the faster you must travel to escape its grip. At the event horizon of a black hole, the escape velocity equals the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever leave. Not light, not matter, not information. The boundary is absolute. It is not a wall or a barrier. There is no physical substance there to block your path. If you could somehow approach an event horizon, you would not feel anything unusual as you crossed it. you would simply continue falling, unaware that you had passed the point of no return. The size of the event horizon depends entirely on the mass of the black hole. More massive black holes have larger event horizons. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a supermassive black hole with 1 billion times the Sun's mass, the event horizon would stretch across billions of kilometers. The larger the black hole, the gentler the environment at the event horizon itself. Smaller black holes have steeper gravitational gradients, while supermassive ones have event horizons where the curvature of space is almost smooth. From the outside, the event horizon appears frozen. If you watched something fall toward a black hole, you would see it slow down as it approached the boundary. It would become redder, dimmer, moving more and more slowly until it seemed to freeze just above the event horizon, never quite crossing it. This is an illusion caused by the way time behaves near the boundary. Light from the falling object takes longer and longer to climb out of the gravitational well, stretching time from your perspective. But from the perspective of the falling object, nothing strange happens. It crosses the event horizon smoothly and continues falling. This difference in perspective is one of the most profound aspects of black holes. There is no single, universal truth about when something crosses the event horizon. From far away, it never quite happens. From close up, it happens in finite time. Both perspectives are correct within their own frames of reference. This is what relativity means in practice. Space and time are not fixed backdrops, but flexible frameworks that bend and stretch depending on where you are and how fast you're moving. The event horizon is the edge that divides space, separating what can return from what cannot. It is a one-way door written into the geometry of the universe itself, a threshold where time changes and the flow of cause and effect becomes permanently altered. Once matter, energy, or information passes through, it joins everything else that has ever fallen in. From that moment on, it exists only as a contribution to the black hole's mass, spin, and charge. Its individual identity is erased, replaced by a simple numerical addition to the black hole's total properties. This erasure is not violent or malicious. It is simply what happens when the geometry of space-time curves so steeply that all paths lead inward. The event horizon does not grab or pull or trap. It simply marks the region from which no future path leads outward. Inside that boundary, every trajectory points toward the singularity. Outside, escape is still possible. The line between them is mathematically precise, determined by the mass of the black hole and nothing else. In a sense, the event horizon is the most patient boundary in the universe. It does not move or change unless the black hole gains or loses mass. It sits in space, waiting with infinite stillness for whatever might approach. Time at the boundary stretches toward infinity. Events there unfold in slow motion from the perspective of distant observers. Yet the boundary itself is timeless, unchanging, marking the same point in space for as long as the black hole exists. Feel the support beneath you. Near a black hole, time behaves in ways that seem impossible. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. This effect, called gravitational time dilation, is not an illusion or a trick of perception. It is a fundamental feature of how time and gravity are woven together. Clocks near a black hole genuinely run slower than clocks far away. If you could stand near the event horizon of a black hole and then return to a distant observer, you would find that far less time had passed for you than for them. This happens because gravity curves not only space but also time. The two are not separate, they are aspects of a single fabric called space-time. When mass curves space-time steeply, time itself stretches. Near a black hole where the curvature is extreme, time dilates dramatically. An hour experienced near the event horizon might correspond to years or even centuries for someone far away. The closer you get, the more pronounced the effect becomes. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer. Time appears to stop. This means that black holes are not only objects in space, they are also objects in time. When you look at a black hole, you are looking at a region where past, present, and future become tangled in ways that defy everyday experience. An astronaut falling toward the event horizon would experience time normally from their own perspective. But to someone watching from a safe distance, the astronaut would appear to slow down, taking an infinite amount of time to actually cross the boundary. The astronaut would seem suspended at the threshold forever, gradually fading from view as their light redshifts into invisibility. This stretching of time has been confirmed in less extreme environments. Satellites in orbit experience slightly less gravity than objects on Earth's surface, and their clocks run slightly faster as a result. The difference is tiny, but it is real and measurable. GPS satellites must account for this time dilation to provide accurate positioning. The same principle applies to black holes, just amplified to astonishing extremes. Where time stretches and bends, the ordinary flow of seconds and hours becomes something fluid and strange. If you could somehow survive near a black hole and observe the universe beyond, you would see time accelerate around you. Stars would age rapidly, galaxies would evolve, the distant cosmos would flicker through its history like a sped-up film. You would exist in a bubble where time moved at one pace, while the rest of the universe raced ahead. This is one of the reasons black holes feel so distant and surreal. They do not simply exist far away in space, they exist in a different relationship with time itself. This temporal distortion also affects light. Photons climbing out of the gravitational well around a black hole lose energy in the process. Their wavelengths stretch, shifting toward the red end of the spectrum. This gravitational redshift is distinct from the Doppler redshift caused by motion. It is a redshift caused purely by the effort of escaping gravity's grip. Light that begins as blue might reach a distant observer as red or infrared or even radio waves, depending on how deep in the gravitational well it originated. The implications of time dilation near black holes extend into physics and philosophy both. If time can slow down, if it can stretch and bend, then it is not the fixed, universal ticking clock we experience in everyday life. It is something more flexible, more responsive to the distribution of mass and energy in the universe. This realization, confirmed through countless experiments and observations, fundamentally changed how we understand reality. Time is not separate from space. It is not immune to the influence of matter. It is woven into the fabric of the cosmos, shaped by every massive object. And nowhere is this shaping more dramatic than near a black hole. Clocks that run at different speeds remind us that our experience of duration is local, personal, tied to our position in the universe's gravitational landscape. There is no absolute now, no universal present moment. There is only the time you experience where you are, flowing at a rate determined by how deeply you sit in the gravitational wells around you. Despite their name, black holes do not suck. This is one of the most common misconceptions. A black hole's gravity behaves exactly like the gravity of any other massive object. It follows the same inverse square law, where the strength of gravity decreases with the square of the distance. If the Sun were instantly replaced by a black hole of equal mass, Earth's orbit would not change. We would continue circling at the same distance, in the same path, experiencing the same gravitational pull. The only difference would be the absence of sunlight. Black holes only become dangerous when you get very close to them. At large distances, their gravity is no different from that of a star or planet of equivalent mass. The reason they seem to trap everything is not because they pull harder than other objects, but because their mass is compressed into such a small space. This compression allows you to get much closer to the center of mass than you could with a normal star. And the closer you get to any massive object, the stronger its gravity becomes. For example, if you approach the Sun, you would eventually reach its surface and could get no closer to its center. But a black hole with the same mass has no surface. You can continue falling inward, getting closer and closer to the center, experiencing stronger and stronger gravity. It is this ability to approach the center so closely that creates the extreme effects associated with black holes. The gravity itself is not unusual. What is unusual is the absence of anything to stop you from falling all the way in. This means that a black hole sitting alone in space poses no threat to distant objects. It does not send out tendrils of gravity to pull things toward it. It does not roam through the galaxy devouring stars. Most black holes are isolated and harmless, drifting quietly through the void. They affect only what comes very near, and in a galaxy as vast as ours, the chances of accidentally encountering one are vanishingly small. The space between stars is so enormous that even millions of black holes scattered throughout the Milky Way would leave most of the galaxy untouched. What black holes do is wait. They sit in their locations, patient and still, exerting gravity that follows the same rules as every other mass in the universe. Pulling only what comes near, they remain part of the cosmic landscape, no more aggressive than a mountain or a canyon. Their darkness is not hunger, it is simply the natural result of gravity becoming concentrated enough to trap light. From a distance, they are gentle reminders that the universe contains objects beyond our everyday experience, yet governed by laws we can understand. The misconception that black holes actively consume everything around them likely comes from their dramatic portrayal in popular media. Images of swirling accretion disks and matter spiraling inward create the impression of a cosmic whirlpool. But these images show what happens only when a black hole has a source of nearby material. Without fuel, without gas or stars passing close by, a black hole is simply invisible, sitting quietly in space with no outward sign of its presence. In fact, you could orbit a black hole safely, just as Earth orbits the Sun, if you maintained a stable orbit at a distance where the gravitational force was balanced by your orbital velocity. You would circle the black hole indefinitely without falling in. Astronauts orbit Earth using the same principle. Earth's gravity pulls them downward, but their forward motion keeps them in a stable path. The same physics applies to black holes. Gravity that follows the same rules means predictable, stable orbits are possible. This understanding removes much of the fear associated with black holes. They are not cosmic predators hunting through space. They are not waiting to trap unwary travelers. They are simply massive objects sitting where they formed or where their motion has carried them, affecting their surroundings through gravity and nothing more. Their influence extends as far as their mass dictates, growing weaker with distance according to the same mathematical relationship that governs every gravitational interaction in the universe. The next time you think of a black hole, imagine not a drain or a vacuum or a monster, but simply a very dense object sitting peacefully in space. Its gravity shaping the paths of nearby matter according to laws that have never changed. Rest your eyes. At the center of nearly every large galaxy, there exists a supermassive black hole. These objects contain millions or even billions of times the mass of the Sun, yet they occupy a region of space no larger than our solar system. The Milky Way, our home galaxy, contains one such black hole at its center. We call it Sagittarius A star, and it has been there for billions of years, quietly anchoring the motion of hundreds of billions of stars. Every star in our galaxy, including the Sun, orbits around this central mass over timescales so vast they dissolve into abstraction. Supermassive black holes are different from their stellar cousins in more than just size. They formed through different processes, likely growing from smaller seeds in the early universe and accumulating mass over billions of years. Some may have formed from the direct collapse of massive gas clouds in the first generation of galaxy formation. Others may have grown by gradually gathering in matter from their surroundings or by merging with other black holes over cosmic timescales. The details remain uncertain, but the result is clear. Nearly every galaxy we observe contains one of these giants at its core. Despite their immense mass, supermassive black holes are not dense in the way you might imagine. Density is mass divided by volume, and because the event horizon of a supermassive black hole is so large, the average density within that boundary can be surprisingly low. For the largest supermassive black holes, the density at the event horizon is less than that of water. You could, in theory, cross the event horizon of such a black hole without immediately noticing anything unusual. The tidal forces there would be gentle. It is only as you continued falling inward that the effects would intensify. These massive hearts of galaxies may play a role in shaping the galaxies themselves. The energy released by matter falling into a supermassive black hole can influence star formation across the entire galaxy. Jets of material, accelerated to nearly the speed of light, can stream outward from the regions around these black holes, carrying energy and momentum across vast distances. The relationship between a galaxy and its central black hole is complex, a balance between destruction and creation that unfolds over billions of years. Observations have revealed a surprising correlation. The mass of a galaxy's central supermassive black hole is closely related to the properties of the galaxy's central bulge. Galaxies with larger, more massive bulges tend to have more massive black holes. This relationship suggests that the black hole and its galaxy grow together, each influencing the other's development. The feedback loop between them helps regulate star formation, gas distribution, and the overall structure of the galaxy. Our own galaxy's supermassive black hole is relatively quiet. It does not consume large amounts of material. It sits in calm equilibrium, a silent anchor around which the Milky Way rotates. We are in no danger from it. Our solar system orbits at a safe distance of about 26,000 light-years, far enough that the black hole's gravity is just one component among many in the gravitational dance of the galaxy. The center we circle in silence has been there since before the sun was born, and it will remain long after the sun fades. The discovery of supermassive black holes transformed our understanding of galactic structure. Before we knew they existed, the motion of stars in galactic centers seemed puzzling. Stars near the cores of galaxies moved faster than expected, suggesting the presence of enormous amounts of invisible mass. As observations improved, the evidence became undeniable. Something incredibly massive and compact sat at the heart of every large galaxy, invisible but exerting tremendous gravitational influence. These objects are not temporary features. They are permanent fixtures of galactic architecture, as fundamental to the structure of galaxies as stars themselves. Over cosmic time, they may grow larger by absorbing gas and stars, or by merging with other supermassive black holes when galaxies collide. But they do not disappear. They persist, organizing the motion of billions of stars around them, shaping the evolution of their host galaxies in ways we are only beginning to understand. In the darkness between stars, something vast and patient is always listening. When matter falls toward a black hole, it does not plunge directly inward. Instead, it spirals, forming a rotating disk of gas and dust called an accretion disk. This disk can stretch across millions of kilometers, glowing brightly as the material within it heats up through friction. As particles orbit closer and closer to the event horizon, they move faster and collide more frequently. These collisions generate heat, raising the temperature of the disk to millions of degrees. At such temperatures, the disk emits intense radiation across the spectrum, from visible light to X-rays. This is why some black holes are among the brightest objects in the universe, even though the black holes themselves emit no light. the accretion disk becomes a beacon, outshining entire galaxies. Astronomers can detect black holes not by seeing them directly, but by observing the brilliant halos of light around darkness that form as matter spirals inward. The light comes not from the black hole itself, but from the material that has not yet crossed the event horizon. It is brightness born from falling, a final blaze of energy before matter disappears from the visible universe. The structure of an accretion disk is shaped by the rotation of the black hole. Most black holes spin, carrying angular momentum from the stars that formed them or the material they have absorbed over time. This rotation drags space-time around the black hole in a process called frame dragging. The inner region of space itself is pulled along with the black hole's spin, forcing everything nearby to rotate in the same direction. The disk aligns with this rotation, creating a thin, flat structure that orbits in the same direction as the black hole's spin. Near the inner edge of the disk, the material moves at a significant fraction of the speed of light, whipped around by the intense gravity. Not all the material in an accretion disk falls into the black hole. Some of it is flung outward in powerful jets that shoot away from the poles of the black hole at relativistic speeds. These jets can extend for thousands of light years, carrying energy and matter far beyond the black hole itself. The mechanism that creates these jets is still not fully understood, but it involves the interplay between the black hole's spin, its magnetic field, and the material in the accretion disk. The jets are narrow and focused, like cosmic searchlights, visible across the universe. The magnetic fields in accretion disks play a crucial role. As charged particles spiral inward, they generate and amplify magnetic field lines. These fields can become twisted and concentrated, eventually launching material outward in collimated jets. The process converts gravitational energy into kinetic energy with remarkable efficiency. In some cases, more than 10% of the infalling matter's rest mass energy is converted into the energy of the jet, a far higher efficiency than nuclear fusion in stars. Accretion disks are not permanent. They form when a black hole has access to material, and they fade when the supply runs out. A black hole that has consumed everything nearby will sit in darkness, invisible and undetectable except through its gravitational influence. But when fresh material arrives, perhaps from a passing star or a cloud of gas, the disk reignites and the black hole blazes back into visibility. These cycles can repeat over millions of years, each time painting light around the void. The colours emitted by accretion disks tell us about their temperature and composition. The hottest regions closest to the black hole emit X-rays and gamma rays. Further out, where temperatures are lower, the disk glows in ultraviolet and visible light. The outer edges might emit infrared radiation. By analysing this spectrum, astronomers can determine the mass and spin of the black hole, the rate at which it is consuming material, and the conditions in the disk itself. Some of the most spectacular objects in the universe are powered by accretion disks around supermassive black holes. Quasars, blazars, and active galactic nuclei all shine with the light of matter, falling toward enormous black holes at the centres of distant galaxies. These objects can outshine all the stars in their host galaxies combined, visible across billions of light years. They are among the most luminous phenomena in the cosmos, testament to the incredible energy that gravity can extract from infalling matter. Let your thoughts drift. For decades, black holes existed only as theoretical predictions. Einstein's equations of general relativity allowed for them, but no one had ever seen one. They were mathematical curiosities, objects that could exist in principle, but might not exist in reality. That changed in April of 2019, when scientists released the first direct image of a black hole's shadow. The image showed a glowing ring of light surrounding a dark circle, exactly as predicted by the mathematics of curved space-time. The black hole itself remained invisible, but its presence was undeniable, outlined by the light bending around it. The black hole in the image resides in a galaxy called Messier 87, located about 55 million light-years from Earth. It is a supermassive black hole, containing more than 6 billion times the mass of the Sun. The event horizon spans a diameter larger than our entire solar system. To capture this image, astronomers used a network of radio telescopes spread across the Earth, effectively creating a telescope the size of the planet. This technique, called Very Long Baseline Interferometry, combines data from multiple telescopes to achieve the resolution of a single enormous instrument. They collected data over several nights, and then spent years processing it, reconstructing the image from the faint radio signals that had travelled across the universe. The ring of light in the image is the accretion disk viewed nearly edge-on. The bottom half of the ring appears brighter than the top because of the black hole's rotation. Material on the side moving toward us is boosted in brightness by relativistic effects, while material moving away is dimmed. This asymmetry confirms that the black hole is spinning and allows scientists to determine the direction and speed of that spin. The shadow itself, the dark circle at the center, is larger than the event horizon. It represents the region from which no light can escape, including light that passed near the event horizon but was bent inward by the intense gravity. This image confirmed what scientists had believed for decades. Black holes are real. They exist as physical objects, not just mathematical abstractions. The shadow we finally saw matched the predictions so closely that it felt less like a discovery and more like a reunion with something we had always known was there. The image also revealed how deeply space-time can be warped. The light forming the ring had been bent through extreme angles, looping around the black hole multiple times before escaping to reach our telescopes. The photon ring visible in the image is actually composed of light from all around the black hole, not just from the parts directly facing us. Gravity bends the light so severely that we can see the far side of the accretion disk wrapped around the edges of the shadow. This lensing effect creates a complete view of the disk compressed into a narrow ring. Some photons orbit the black hole one or more times before escaping, creating fainter inner rings that are barely visible in the image but present in the data. Since that first image, astronomers have captured another, this time of Sagittarius, a star, the black hole at the center of our own galaxy. Though closer to the Messier 87 black hole, Sagittarius A star is much smaller and more variable, making it harder to image. The material around it orbits so quickly that it changes on timescales of minutes, requiring sophisticated techniques to average out the variations and extract a stable image. But the result was the same: a glowing ring surrounding a dark circle, light bending into view in perfect agreement with the predictions of general relativity. These images are not just scientific achievements, they are reminders that the universe contains wonders we can reach toward, even when those wonders are so distant and strange that light itself struggles to carry their story to us. The collaboration required to create these images involved hundreds of scientists from dozens of countries working together to point instruments at the same target and combine their data into something no single telescope could achieve alone. The shadow at the center of each image is a testament to human curiosity and cooperation, proof that we can see the unseeable when we work together. The images also serve a deeper purpose. They connect the abstract mathematics of general relativity to visual reality. They transform equations into pictures, making the invisible visible and confirming that our understanding of gravity extends even to these extreme environments. At the center of the Milky Way, hidden behind clouds of gas and dust, sits Sagittarius A star. It is a supermassive black hole containing about 4 million times the mass of the Sun. Though immense by terrestrial standards, it is relatively small compared to other supermassive black holes. It is also remarkably quiet. Unlike some black holes that blaze with light from their accretion disks, Sagittarius A star consumes very little material. It sits in calm equilibrium, a gentle presence at the heart of our galaxy. We cannot see Sagittarius A star with visible light because the galactic center is obscured by dense clouds of interstellar dust. The dust absorbs and scatters visible light, making the core of the Milky Way opaque in optical wavelengths, but we can observe it using radio waves and infrared light, which penetrate the dust more easily. Astronomers have been watching the region around Sagittarius A star for decades, tracking the motion of stars that orbit close to it. These stars move incredibly fast, some completing orbits in just a few years despite travelling paths that span billions of kilometres. By measuring their trajectories, scientists have been able to calculate the mass of the object they orbit. The conclusion is inescapable. There must be a supermassive black hole there, even though we cannot see it directly. One of these stars, known simply as S2, has an elliptical orbit that brings it within about 17 light hours of Sagittarius A star at its closest approach. A light hour is the distance light travels in 1 hour, about 1 billion kilometers. When the star swings near the black hole, it accelerates to nearly 3% of the speed of light. Its orbital period is about 16 years, meaning astronomers have been able to watch it complete multiple orbits since observations began. These observations have confirmed predictions of general relativity with remarkable precision, including subtle effects like the precession of the orbit and gravitational redshift of the star's light. The precession of S2's orbit is particularly interesting. In Newtonian gravity, a planet orbiting a star follows a perfect ellipse that repeats exactly with each orbit. But in general relativity, the ellipse itself slowly rotates. The long axis of the ellipse shifts slightly with each orbit, a phenomenon called precession. This effect was first observed in Mercury's orbit around the Sun, and was one of the early confirmations of general relativity. For us two orbiting Sagittarius A star, the precession is much larger and easier to measure, providing another test of Einstein's theory in a strong gravitational field. Despite its size and proximity, Sagittarius A star poses no threat to us. The solar system orbits the galactic center at a distance of about 26,000 light-years. At that range, the black hole's gravity is just one of many forces shaping the galaxy's structure. Our orbit takes about 230 million years to complete. We orbit it the same way the Earth orbits the Sun, in a stable, predictable path that has persisted for billions of years and will continue for billions more. The black hole is part of the architecture of our galaxy, a central mass that helps organize the motion of stars, but it is not an active threat. Observations of Sagittarius A star have also revealed occasional flares of X-ray and infrared emission. These flares likely come from hotspots in the accretion disk or from magnetic reconnection events near the event horizon. They brighten for a few hours and then fade, leaving the black hole in its usual quiet state. The exact cause of these flares is still being studied, but they provide glimpses into the dynamics of the material closest to the event horizon. The quiet anchor of our galaxy has become one of the best laboratories for testing our understanding of gravity. Because it is relatively close, and because we can observe stars orbiting it with high precision, Sagittarius A star allows us to study general relativity in conditions that cannot be replicated anywhere else in the solar system. Every measurement of a star's orbit, every observation of a flare, adds to our understanding of how gravity behaves near a supermassive black hole. Sagittarius A star reminds us that black holes are not merely destroyers. They are also anchors, organizers, participants in the structure of galaxies. Ours has been patient and quiet for as long as we have existed as a species. It will remain so long after we are gone, continuing its slow work of holding the galaxy together, invisible and distant but always present. Feel the stillness. There is a term in astrophysics that sounds alarming but describes a surprisingly gentle process when viewed in context: spaghettification. It refers to what happens when the difference in gravitational pull between two ends of an object becomes so large that the object is stretched. Near a black hole, this tidal effect can become extreme. If you were falling feet first toward a black hole, your feet would experience stronger gravity than your head because they are closer to the source. This difference pulls you into a long, thin shape, much like stretching dough or taffy. The name sounds violent, but the process is simply gravity's gradient stretching space. Whether you would experience spaghettification depends on the size of the black hole. For a small stellar mass black hole with just a few times the Sun's mass, the tidal forces near the event horizon are intense. The difference in gravity between your head and feet would be enormous. and you would be stretched long before you reached the boundary. The forces would become uncomfortable far outside the event horizon and destructive well before you actually crossed it. But for a supermassive black hole, the event horizon is so large that the tidal forces there are surprisingly mild. You could cross the event horizon of the largest supermassive black holes without being stretched at all. The gentle pull that shapes would only become significant much closer to the singularity. This is one of the paradoxes of black holes. The larger they are, the less dramatic the experience of falling into them becomes, at least initially. A stellar mass black hole would tear you apart from tidal forces well outside the event horizon. But a supermassive black hole would allow you to fall through the event horizon intact, experiencing nothing unusual in those first moments. It is only deeper inside as you continued falling toward the singularity where all mass is concentrated that the tidal forces would grow overwhelming. By then, of course, you would be far beyond any possibility of escape or communication. Spaghettification is not unique to black holes. Any sufficiently strong gravitational gradient can produce tidal effects. The moon creates tides on Earth through the same principle. The side of the Earth facing the moon experiences slightly stronger gravity than the side facing away, pulling the oceans into an elliptical shape. Near a black hole, this same effect is simply magnified until it becomes the dominant force, reshaping anything that falls inward. The physics is the same, only the magnitude changes. From a distance, spaghettification is a poetic reminder of how gravity works. It does not pull uniformly. It pulls with a strength that depends on distance, following the inverse square law that governs all gravitational interactions. When distances become small enough and masses become large enough, that variation becomes a force of transformation. The process is not cruel or hostile. It is simply the natural consequence of curved space-time, a reminder that everything near a black hole must learn new shapes, dictated by the gradient of gravitational acceleration. The term itself comes from the resemblance to spaghetti noodles, long and thin. In technical literature, it is sometimes called the noodle effect or tidal stretching, but spaghettification has become the popular term. Despite its whimsical sound, it describes a real physical process that would occur in the extreme gravitational fields near compact objects. The stretching is differential. Every part of an extended object experiences a slightly different gravitational pull, and those differences add up to produce the elongation. For objects falling into stellar mass black holes, spaghettification would be catastrophic. Solid materials would be torn apart. Even atomic bonds would eventually fail under the strain, as the tidal forces grew large enough to overcome the electromagnetic forces holding matter together. But for objects crossing into supermassive black holes, the passage through the event horizon could be almost gentle, with disruption coming only later as the singularity approaches. Understanding spaghettification helps clarify what makes black holes extreme. It is not just the strength of their gravity at a given distance. It is the combination of strong gravity and the ability to get close enough to experience the full gradient. A neutron star has incredibly strong gravity at its surface, but you cannot get closer than that surface. A black hole has no surface to stop you, allowing you to continue falling to regions where the gravitational gradient becomes truly extreme. Black holes do not last forever. In 1974, physicist Stephen Hawking showed that black holes can slowly emit radiation through quantum effects near the event horizon. This radiation, now called Hawking radiation, arises from the strange behavior of empty space according to quantum mechanics. Even in a perfect vacuum, particle-antiparticle pairs constantly flicker into existence and annihilate each other almost immediately. This process happens everywhere in space, all the time, but usually leaves no observable trace because the pairs cancel out. Near the event horizon of a black hole, something different can happen. One particle of a pair might fall inward across the event horizon, while the other escapes to infinity. From an outside perspective, it appears that the black hole has emitted a particle. The escaping particle carries energy away from the black hole, and since energy and mass are equivalent according to relativity, the black hole loses mass over time. This slow leakage of energy causes the black hole to gradually shrink, a process called evaporation. The process is extraordinarily slow for any black hole we have observed or are likely to observe. For stellar mass black holes, the time required to evaporate completely is far longer than the current age of the universe. A black hole with 10 times the mass of the Sun would take more than 10 to the power of 67 years to disappear through Hawking radiation alone. The universe itself is only about 14 billion years old, roughly 10 to the power of 10 years. The evaporation time is so vast it becomes almost meaningless to human comprehension. For supermassive black holes, the evaporation time is even longer, stretching into timescales so immense they dwarf even the longest geological epochs. Yet the principle remains. Even darkness learns to glow, given enough time. Black holes are not eternal prisons. They are temporary structures subject to the same quantum laws that govern all matter and energy in the universe. As they emit Hawking radiation, they shrink. The smaller they become, the faster they radiate. The radiation rate is inversely proportional to the square of the black hole's mass, meaning that smaller black holes evaporate faster than larger ones. In the final moments of a black hole's life, assuming nothing else falls in to replenish it, it would shine brilliantly, releasing all its remaining energy in a sudden burst before vanishing completely. This slow return of light means that black holes are part of the universe's long cycle of transformation. Matter falls in, increasing the black hole's mass. Over unimaginable spans of time, energy trickles back out as Hawking radiation. Nothing is truly lost forever, at least in terms of energy. Everything that enters a black hole contributes to its mass, and therefore to the Hawking radiation it eventually emits, though the information about what specifically fell in may be scrambled beyond recognition. The process connects the quantum world of particles to the cosmic scale of black holes, bridging two realms of physics that seem impossibly distant from each other. For now, Hawking radiation remains purely theoretical, in the sense that it has never been directly observed from an actual black hole. The effect is so faint that the radiation from any black hole we could detect is far weaker than the cosmic microwave background radiation that fills all of space. A black hole would actually absorb more radiation from the cosmic background than it emits through Hawking radiation, meaning black holes are currently growing, not shrinking. Only in the far future, when the universe has expanded and cooled, and the cosmic microwave background has faded to nearly nothing, would Hawking radiation become the dominant effect. But the mathematics are convincing, and the principle is elegant. The prediction arises naturally from combining quantum mechanics and general relativity near the event horizon. It suggests that black holes have a temperature incredibly small but non-zero, and that they radiate like black bodies according to that temperature. Even the darkest objects in the universe carry within them the seeds of their own dissolution, a reminder that nothing in nature is permanent, not even the structures that seem most absolute and final. You don't need to follow every detail. Black holes are often portrayed as destroyers, but they also play a role in creation. The energy released by supermassive black holes can shape their host galaxies in profound ways. When material falls into a black hole and forms an accretion disk, some of that material is flung outward in powerful jets that can travel thousands of light years. These jets carry enormous amounts of energy, ploughing through the surrounding gas and compressing it. As the jets plough through clouds of gas in the galaxy, they compress that gas. When gas is compressed, its density increases, and once it reaches a critical density, gravity can take over and begin pulling it together into clumps. These clumps can become dense enough to ignite nuclear fusion, and new stars are born. This process means that destruction seeds new birth. The same black hole that consumes matter also redistributes energy, stirring the gas and dust of its galaxy, triggering waves of star formation that might not have occurred otherwise. The relationship between black holes and their galaxies is not one-sided. Black holes grow by gathering in material, and in doing so they influence the very structures that feed them. A galaxy and its central black hole evolve together, each shaping the other's development over billions of years. There is even evidence that the mass of a galaxy's central black hole is closely related to properties of the galaxy itself, such as the velocity dispersion of stars in the galactic bulge. Velocity dispersion measures how fast stars are moving in random directions, which reflects the total mass and gravitational potential of the bulge. Galaxies with more massive black holes tend to have stars that move faster in their central regions. This correlation suggests a deep connection, a feedback loop where the growth of the black hole and the growth of the galaxy are intertwined. The mechanisms behind this connection are still being studied, but the pattern is clear across many galaxies of different sizes and types. In this way, black holes are not isolated objects. They are participants in the ecology of the cosmos, connected to star formation, galactic evolution, and the distribution of matter across the universe. The cycle that continues links the smallest scales, where particles collide in accretion disks, to the largest scales where galaxies form and evolve. Black holes sit at the center of this cycle, both literally and metaphorically, gathering in the old and helping to shape the new. The jets they produce can also prevent star formation by heating gas to temperatures too high for it to collapse under gravity. This creates a balance. too much black hole activity, and star formation is suppressed. The galaxy exhausts its ability to make new stars. Too little activity, and the galaxy may form stars too rapidly, using up its gas supply without regulation. The black hole acts as a kind of thermostat, regulating the conditions for star birth across its galaxy. It is a role that seems almost deliberate, though it arises purely from the physics of gravity, thermodynamics, and energy transfer. Observations of distant galaxies show this balance in action. Galaxies with the most actively feeding black holes, known as active galactic nuclei, often show both enhanced star formation in some regions and suppressed star formation in others. The jets heat gas in some areas while compressing it elsewhere. The net result is a galaxy whose star formation rate is regulated by the activity of its central black hole, creating a complex interplay between creation and consumption. Understanding this relationship has changed how astronomers think about galaxy evolution. Black holes are not just endpoints where matter disappears. They are active participants in the ongoing life of their galaxies. They regulate gas flow, trigger or suppress star formation, and influence the chemical composition of the interstellar medium through the material they eject. Every galaxy tells a story not just of stars and gas, but of the central black hole that has shaped its growth over billions of years. As we understand more about this connection, we see that the universe is deeply interconnected. Events on the smallest scales affect the larger structures, and the larger structures in turn create conditions for events on small scales. Black holes, sitting at the boundary between stellar and galactic scales, embody this interconnection perfectly. Let your shoulders soften. When two black holes orbit each other, they gradually lose energy by emitting gravitational waves, ripples in the fabric of space-time itself. These waves travel outward at the speed of light, carrying information about the masses, spins, and orbital parameters of the black holes that created them. As the black holes lose energy to gravitational radiation, their orbits decay. They spiral closer together, orbiting faster and faster, emitting stronger and stronger waves. Eventually they merge, combining into a single, larger black hole in an event that releases more energy in a fraction of a second than all the stars in the visible universe emit in the same time. Gravitational waves were predicted by Einstein's general relativity more than a century ago, but they were not directly detected until September of 2015, when the LIGO Observatory recorded the merger of two black holes for the first time. The signal was faint, a tiny distortion in space-time that stretched and squeezed the detectors by less than the width of a proton, but it was unmistakable, matching the predictions of general relativity so precisely that there could be no doubt. The waveform showed exactly the pattern expected from two black holes spiraling together and merging, a chirp that rose in frequency and amplitude before cutting off abruptly as the merger completed and the ring-down began. The universe had spoken, and we had finally learned how to listen. That first detection opened a new window on the cosmos. For the first time, we could observe events that emit no light, no electromagnetic radiation of any kind. We could detect the merger of black holes billions of light years away, events that would otherwise remain completely invisible. The gravitational waves carried information across the universe without being absorbed, scattered, or altered by the matter they passed through, delivering a pure signal from some of the most violent events in nature. Since that first detection, dozens more gravitational wave events have been observed. Most involve black hole mergers, though some involve neutron stars colliding or a black hole merging with a neutron star. Each detection adds to our understanding of how common these events are, how black holes are distributed throughout the universe, and what happens during the merger process itself. The data has revealed black holes with masses that surprised astronomers, including several in a range that were thought to be rare or difficult to form. The waves themselves are fascinating. Unlike light, which can be absorbed or scattered by dust, gas, or other material, gravitational waves pass through matter almost unimpeded. They interact so weakly with ordinary matter that they carry their signal across billions of light years without losing clarity. When a gravitational wave from a distant merger passes through Earth, it stretches space in one direction and compresses it perpendicular to that direction, oscillating at the frequency of the original event. The effect is incredibly tiny, but with sensitive enough instruments it can be measured. The detectors that sense these waves are marvels of engineering. LIGO consists of two L-shaped facilities thousands of kilometers apart, each with arms several kilometers long. Laser beams bounce back and forth along the arms, and any change in the arm lengths caused by a passing gravitational wave creates an interference pattern that can be detected. The instruments are so sensitive they can measure changes in distance smaller than 1,000th the width of a proton. Isolating such tiny signals from background noise requires sophisticated data analysis and cross-checking between multiple detectors to confirm that a signal is real. These vibrations in the fabric of space remind us that black holes are not isolated. They are connected to the rest of the universe through space-time itself. When they merge, the universe rings like a bell, and we are learning to hear its tones. The study of gravitational wave astronomy is still young, but it has already reshaped our understanding of black holes and the cosmos they inhabit. Each new detection is a message from the universe, written not in light, but in the language of space-time geometry itself. In the darkness between stars, something vast and patient is always listening. Black holes are far more common than most people realize. Our galaxy alone likely contains tens of millions of stellar mass black holes, scattered throughout its spiral arms and halo. Most of these are invisible, drifting quietly through space with no companion stars to illuminate them. They are remnants of massive stars that died long ago, now reduced to points of intense gravity that betray their presence only when something passes close enough to be affected. These silent wanderers make up a significant but hidden population in the Milky Way's census of objects. Despite their numbers, the galaxy is so vast that encountering one is extraordinarily unlikely. The average distance between stars in our region of the Milky Way is about 4 light-years, a gulf so enormous that it takes light itself 4 years to cross it. Black holes are even more spread out, and their gravitational influence is limited to their immediate surroundings. You could travel through the galaxy for billions of years without coming close to one. They are common as old stars, yet the space they occupy is vanishingly small compared to the emptiness around them. The galaxy is mostly empty space, and black holes, numerous though they may be, do not significantly alter that emptiness. Some black holes do have companions. In these binary systems, a black hole orbits a star, sometimes pulling gas from the star's outer layers through a process called Roche-Lobe overflow. When the star expands or when orbital dynamics bring material close to the black hole, gas can flow across the gravitational boundary and begin spiraling into the black hole. This gas forms an accretion disk around the black hole, heating up and emitting X-rays that we can detect from Earth. By studying these X-ray binaries, astronomers have confirmed the existence of many stellar mass black holes and measured their properties. Each discovery adds another data point, helping us understand the population of black holes in the galaxy. Beyond stellar mass black holes, there are the supermassive ones at the centers of galaxies, and possibly intermediate mass black holes that fall between the two categories. Intermediate mass black holes, if they exist, would have masses ranging from hundreds to thousands of times that of the Sun. Evidence for them remains tentative but intriguing. Some globular clusters, dense spherical collections of stars, show kinematic evidence suggesting a massive but unseen object at their centers. Some ultraluminous X-ray sources may be powered by intermediate mass black holes accreting material. Their existence would fill a gap in our understanding, connecting the smallest and largest black holes through a continuum of masses. Theoretical models suggest several ways intermediate mass black holes could form. They might result from the direct collapse of very massive stars in the early universe, before such stars had been enriched with heavy elements that would change their evolution. They might form from the merger of many stellar mass black holes in dense stellar environments like globular clusters. They might be the seeds from which supermassive black holes grow, intermediate steps in a process that takes billions of years to complete. Finding and confirming intermediate mass black holes is an active area of research. Black holes are not anomalies. They are natural endpoints of stellar evolution, as common and inevitable as white dwarfs or neutron stars, just rarer because they require more massive progenitor stars. The universe has been creating them for billions of years, and it will continue to do so as long as massive stars are born. Every star with more than about 25 solar masses will likely end as a black hole, and the formation rate of such stars means that new black holes are constantly being added to the galactic population. Quiet travelers through the dark, they are woven into the fabric of the galaxy, part of its history and its future. Most will exist for timescales longer than the current age of the universe, patient and unchanging, waiting in silence. Some will eventually merge with other black holes, creating gravitational waves that ripple across space-time. Others will drift alone through the expanding cosmos, growing colder and darker as the universe ages around them, until eventually, in a future almost too distant to imagine, they evaporate away through Hawking radiation, returning their mass energy to the universe that created them. One of the deepest puzzles in physics involves black holes and information. According to quantum mechanics, information cannot be destroyed. Every particle, every interaction, every quantum state carries information that must be preserved, even as it transforms through physical processes. The universe keeps track of its details, but black holes seem to violate this rule. When something falls past the event horizon, it disappears from the observable universe. All information about its internal structure, its quantum state, its history, seems to be lost behind the boundary. This contradiction is known as the information paradox. Stephen Hawking's discovery of black hole radiation deepened the paradox. If black holes evaporate over time, releasing only thermal radiation that appears to carry no specific information about what fell in, then the information seems to be permanently erased. Yet quantum mechanics insists that this cannot happen. The resolution of this paradox remains one of the great unsolved problems in theoretical physics. Some scientists believe that information is somehow encoded in the Hawking radiation in ways too subtle to currently detect or understand. Others propose that it is stored on the event horizon itself, perhaps in a holographic pattern that preserves all the details of what fell in across the two-dimensional surface. The question is not urgent in any practical sense. No experiment can test these ideas directly with current technology. The stakes are purely theoretical, concerning the deep foundations of physical law, rather than anything that affects everyday life or even astronomical observation. Yet the paradox touches on fundamental questions about the nature of reality, the limits of physical law, and the relationship between gravity and quantum mechanics. It is a mystery that invites patience rather than anxiety, questions without urgency. The universe does not demand that we solve it immediately. It has waited billions of years already, and will wait billions more. The paradox exists at the intersection of our two most successful theories: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles and fields on the smallest scales. These two theories are both incredibly accurate within their domains, yet they seem incompatible when applied together in extreme environments like the interior of a black hole or the first moments of the Big Bang. In some ways, the information paradox is a reminder that our understanding is incomplete. We have powerful theories that describe the very large and the very small, but we do not yet have a theory that seamlessly unites them. Black holes exist at the intersection of these two realms, and they reveal the boundaries of what we currently know. The mystery of what remains is not a failure of science, but an invitation to keep looking, to remain curious, and to accept that some questions live comfortably in the space between answers. For those of us far from the frontier of theoretical physics, the paradox is simply another facet of the wonder that black holes inspire. They are not fully understood, and perhaps they never will be. That uncertainty does not diminish them. If anything, it makes them more compelling, proof that the universe still holds secrets beyond our reach. The peace of unanswered questions can be its own kind of comfort, a reminder that not everything needs to be known or solved. The paradox also highlights something beautiful about the scientific process. Science does not claim to have all answers. It proceeds by identifying what we do not understand and working patiently toward better understanding. The information paradox has driven decades of theoretical work, inspiring new ideas about quantum gravity, string theory, and the holographic principle. Even without a definitive resolution, the question has been productive, leading to insights that extend far beyond black holes themselves. In the end, the information paradox may be resolved, or it may remain open, or it may transform into a different question entirely as our understanding evolves. Whatever happens, it serves as a reminder that the universe is under no obligation to make sense to us. We are simply fortunate that it makes as much sense as it does, and that we have the capacity to ask these questions at all. Not knowing and needing nothing more, we can rest in the knowledge that mystery is part of the landscape of existence. In a way, black holes are archives. Everything that falls into one contributes to its mass, spin, and electric charge. These three properties, known collectively as the black hole's parameters, encode the cumulative history of everything the black hole has consumed. A black hole remembers, in a sense, though its memory is impersonal and profoundly simplified. It does not retain the details of what fell in, only the total contributions to its defining numbers. The texture of a star, the composition of a planet, the quantum state of every particle. All these details are erased, leaving only mass, spin, and charge. This idea is sometimes expressed with the phrase that black holes have no hair, meaning that black holes are simple objects defined entirely by a small set of numbers. Two black holes with the same mass, spin, and charge are indistinguishable, regardless of what formed them or what they have absorbed over their lifetimes. A black hole created from a collapsing star is identical to one created from compressed gas or from the merger of other black holes, provided the parameters match. The individuality of the matter that created them is lost, replaced by an elegant, almost austere simplicity. Yet there is something profound in this simplicity. Every particle, every photon, every atom that crosses the event horizon becomes part of the black hole's mass. In that sense, black holes carry memory held in gravity, a cumulative record of their interactions with the universe. They are shaped by their history, even if the details of that history are erased. The structure they possess is a story written in mass, a biography compressed into fundamental numbers that describe curvature and rotation. This makes black holes both impersonal and intimate at the same time. They consume without preference, treating starlight and cosmic dust with equal indifference, gathering in whatever comes near without judgment or selection. Yet every contribution changes them, adding to their mass or spin, altering their event horizon, shifting their relationship with the space-time around them. They are archives that forget details but remember totals, objects that grow by accumulation, and carry within them the integrated influence of everything they have encountered. For the universe, this serves a kind of purpose. Black holes simplify complexity. They take the intricate arrangements of matter and energy, all the baroque details of stars and planets and gas clouds, and reduce them to a handful of values. In doing so, they create objects that are predictable and mathematically tractable, despite their origins in chaos and catastrophe. They are natural summarizers, distilling the past into a form that can be described with precision and elegance. The loss of information may seem tragic from one perspective. All the complexity of a star's composition, all the unique arrangements of atoms that made it different from every other star, vanish when the star collapses into a black hole. But from another perspective, this simplification is beautiful. It reveals that beneath all the surface complexity of the universe, there are deeper patterns and symmetries. Black holes strip away the accidents of history and show us what remains: mass, angular momentum, and charge. The essential properties that define how an object curves space-time. This archival nature also means that black holes are not separate from the universe's history. They are part of it, carrying traces of every interaction encoded in their parameters. A supermassive black hole at the center of a galaxy has grown over billions of years, accumulating mass from countless sources. Its current mass tells you how much material has fallen in. Its spin tells you about the direction and angular momentum of that material. The black hole is a record of its galaxy's feeding history, a testament to billions of years of accretion, mergers, and interactions. Stories written in mass are still stories, even if they are told in a language of numbers and geometry rather than words and images. When we measure a black hole's properties, we are reading that story, interpreting what the black hole has become as a result of everything it has consumed. In this sense, every black hole is unique, not because of internal structure we can observe, but because each one has followed a different path through cosmic history, gathering in different amounts and types of material, spinning up or down through interactions we can only infer. It's all right if your mind wanders. One of the most comforting things about black holes is their patience. They exist on timescales so vast that human concerns dissolve into perspective. A black hole can sit in space for billions of years, essentially unchanged, while galaxies evolve around it. Stars are born and die, planets form and scatter, entire civilizations could rise and fall, species could emerge, flourish and vanish. And through all of it, the black hole persists, continuous and still, measuring time in units that mock the brevity of human experience. This patience is not passive. It is not the patience of waiting for something to happen. It is the patience of deep structure, the kind that emerges from fundamental laws rather than conscious choice. A black hole does not wait because it decides to. It waits because it exists in a framework where time moves differently, where change happens on scales that extend beyond imagination. To stand in the presence of such timescales, even conceptually, is to feel the weight of the temporary lifted. Your worries, your plans, your entire lifespan becomes a flicker against the backdrop of cosmic endurance. There is something deeply calming in this. The universe does not need you to hurry. It does not measure success by speed or productivity or the frantic pace of modern life. It simply continues, and in continuing it offers a model of existence that values persistence over urgency, continuity over change. Black holes embody this. They are content to exist, gathering in what comes near, radiating slowly through quantum effects too faint to measure. participating in the life of the galaxy without impatience or haste. Patience measured in eons is the only patience they know. They do not count days or years. They barely notice the passage of centuries. 1,000,000 years is nothing to a black hole, a brief moment in its vast existence. This perspective can be a gift to someone lying awake at night, caught in the tangle of immediate concerns. The things that feel urgent tonight will pass. The struggles that seem overwhelming will fade. Not because they are unimportant, but because time itself is a river that carries everything forward, dissolving sharp edges, softening hard moments, transforming everything it touches. Black holes are proof that the universe has room for slowness, for waiting, for the gradual unfolding of events across incomprehensible spans. They remind us that not everything happens quickly, that some processes take longer than the age of stars, and that patience itself can be a form of strength. In a culture that often prizes speed and immediate results, black holes stand as monuments to the power of persistence, of simply continuing to exist without rush or anxiety. They also remind us that endings are not final. A black hole is the endpoint of a star's life, yet it is also the beginning of something new. It shapes its surroundings, influences its galaxy, and eventually, in timescales we can barely conceive, returns its energy to the universe through Hawking radiation. Even in their stillness, they participate in cycles of transformation that stretch from the quantum scale to the cosmic. They are both archive and seed, both memory and potential, existing in a state that transcends the simple binary of alive and dead, present and absent. The comfort of black hole patience lies in recognizing that urgency is optional. Time will unfold whether we rush or rest. The universe operates on its own schedule, indifferent to our deadlines and anxieties. By aligning ourselves with that larger rhythm, even conceptually, we can find a kind of peace. We can let go of the need to force immediate solutions and instead trust that time, given enough of it, resolves most things on its own. Black holes teach us that waiting is not weakness, stillness is not stagnation, patience is not passivity. They are forms of strength that operate on different timescales than we are used to, but they are no less powerful for that. When you feel rushed or pressured, remember that somewhere in the cosmos black holes are simply existing, patient and calm, proving that the universe itself knows how to wait. And if the universe can wait, perhaps we can too, at least for tonight, at least until sleep comes and the morning brings whatever it will bring. Feel free to let the words wash over you. When you look at a black hole, you are looking backward in time. This is true of everything you see in the night sky, but it feels especially meaningful with black holes. Light takes time to travel, and the farther away an object is, the longer its light has been journeying toward you. The black hole you observe through a telescope or in an image is not as it is now, but as it was when its light began its journey, perhaps millions or billions of years ago. You are seeing an echo, a frozen moment preserved in photons that have travelled across the universe to reach your eyes or our instruments. This means that telescopes are time machines of a sort. They allow us to see the universe as it was, not as it is. When astronomers study distant black holes, they are studying the past, observing events that unfolded long before humans existed, long before Earth had cooled enough for oceans to form. The light bending into view around those event horizons may have left its source when the solar system was just a disk of gas and dust, or when the first single-celled organisms were beginning to emerge in ancient seas, or even earlier, when the universe itself was younger and smaller. The universe we see is a patchwork of different eras, layered together by the finite speed of light. Nearby objects show us the recent past, distant objects show us the ancient past, and the farther we look, the further back in time we see. The most distant black holes we can observe existed when the universe was a fraction of its current age, when the first galaxies were just forming and the cosmic conditions were dramatically different from today. Their light has been travelling toward us for most of the universe's history. This creates a strange kind of intimacy with the past. The photons entering your eye or our detectors tonight travelled across the void for unimaginable spans, carrying information about the state of a black hole in an age you will never visit, in a galaxy you will never approach. They crossed other galaxies, passed through clouds of gas, bent around massive objects, all to arrive here, now, and tell you something about what once was. In observing, you become a receiver of history, a participant in a conversation that began long before you were born and will continue long after you're gone. For black holes, this effect is even more layered. Because time dilates near their event horizons, the light we see from their surroundings has been affected by that dilation. Events near the black hole unfold more slowly from our perspective, stretched by gravity into a kind of temporal fog. We see them as if through a lens that distorts not just space but time itself. The windows to the ancient past that black holes provide are warped and strange, showing us not just the distant past but a past that moved at a different pace, where time itself flowed differently than it does here. This layering of time is part of what makes black holes so compelling. They are not just objects in space but markers in time, monuments to the universe's history visible to us only because light carries that history forward. To study them is to study the past, to trace the evolution of the cosmos through the evidence that reaches us, photon by photon, across the vast and patient dark. Every image of a black hole is an image of history, a snapshot of conditions that existed in a different era. And yet, somewhere out there, those black holes still exist, continuing their work in the present moment we cannot see. They have evolved since their light left them. They may have consumed more matter, merged with other black holes, or simply persisted in quiet equilibrium. We will not know their current state for millions or billions of years, when the light they are emitting now finally reaches us. The present of a distant black hole is inaccessible to us. We are forever locked into observing its past. This disconnect between observation and reality is one of the fundamental constraints of astronomy. We cannot see the universe as it is. We can only see it as it was, with the delay proportional to distance. Light that carries history is all we have, and black holes, with their extreme effects on time and space, make that history both richer and stranger. Black holes exist at the boundary of what physics can currently describe. They challenge our theories in ways that few other objects do. At the event horizon, general relativity reigns, describing gravity as the curvature of space-time with equations that have been tested and confirmed countless times. But at the singularity, where density becomes infinite and space-time curvature becomes undefined, general relativity breaks down. The equations produce infinities, a mathematical sign that something is missing from our description. Quantum mechanics, which governs the behavior of particles on the smaller scales, may hold the key to understanding what truly happens at the center of a black hole. But we do not yet have a complete theory of quantum gravity. This is not a failure. It is simply where we are. Science progresses by testing ideas against reality, and black holes are among the most extreme realities we have found. They push our theories to their limits, revealing gaps and inconsistencies that point the way toward deeper understanding. In the darkness between stars, something vast and patient is always listening. The fact that we cannot fully describe a black hole's interior does not mean we understand nothing. It means we understand enough to know what we do not yet understand, which is itself a kind of knowledge, a map that shows not just the territory we have explored, but also the regions that remain beyond our current reach. For most purposes, this incompleteness does not matter. We can predict the behavior of black holes with remarkable accuracy using general relativity alone. We can describe their formation, their growth, their interactions with surrounding matter, their slow evaporation through Hawking radiation, and their mergers with other black holes. The mysteries at the singularity are important for theoretical physics, but they do not prevent us from studying and understanding black holes in practical terms. The beautiful limit of knowing is still rich with insight. There is also a kind of peace in accepting that some things may remain beyond our reach. Not every question has an answer, at least not an answer we can access with our current tools and understanding. Not every mystery needs to be solved, at least not in our lifetimes, or perhaps ever. The universe has been generous in revealing as much as it has. Black holes, in their inscrutability, remind us that we are part of a cosmos far larger and stranger than we can fully comprehend. This does not diminish us. It places us in context, offering humility as a counterbalance to ambition. As you rest here, consider that the edges of understanding are not failures but invitations. The questions that remain are not burdens but opportunities, chances for future minds to explore, to wonder, and to discover. Some questions may never be answered, and that is acceptable. The universe is not obligated to be comprehensible to us. We are simply fortunate that we can understand as much as we do, that the mathematical language we have developed describes so much of reality with such precision. The universe is patient with its secrets, and so can we be. There is no rush. The black holes will still be there, waiting, long after we have moved through all the questions we can ask in this lifetime. They will persist as they always have, marking the boundaries between what we know and what remains unknown, between the physics we have mastered and the physics we have yet to discover. Questions rest peacefully in the space they occupy, neither demanding immediate answers nor fading into irrelevance. Black holes teach us that uncertainty is not something to fear. It is simply part of the landscape of existence. Every generation of scientists inherits questions from the previous one and passes new questions to the next. Progress happens gradually through patience and persistence, through careful observation and creative thinking. The questions surrounding black holes have driven some of the most profound theoretical work in physics, inspiring new mathematical frameworks and new ways of thinking about space, time, matter, and information. In their mystery, black holes remain generous. They give us puzzles to solve, phenomena to explain, and boundaries to push against. They remind us that there is always more to learn, always deeper questions to ask. And in that reminder, they offer not frustration but wonder, not limitation but possibility. Where questions rest peacefully, we can rest too, knowing that not everything needs to be understood tonight. Feel your breathing slow. Black holes teach us that darkness isn't emptiness, but transformation. When a star collapses into a black hole, its light disappears, but its mass remains. The atoms that once made up the star persist within the event horizon, contributing to the black hole's gravitational presence. Nothing is destroyed, only changed into a different form, concentrated and hidden, but still part of the universe's total inventory of matter and energy. This transformation reminds us that endings are not obliterations. They are transitions into states we may not fully understand, but that remain part of the ongoing story. The darkness of a black hole is not the darkness of absence or void or threat. It is the darkness of concentration, of gravity becoming so focused that even light must follow its pull. It is a darkness that results from following natural law to its logical conclusion, from allowing gravity to do what it does without resistance. There is nothing malevolent in this darkness. It is simply the state that emerges when certain conditions are met, as natural as the darkness of night or the darkness of a cave, just operating under more extreme circumstances. This distinction matters when we think about darkness in our own lives. We often use darkness as a metaphor for fear, loss, or unknowing. But black holes suggest a different metaphor. Their darkness is a sign of transformation, a region where the rules change but do not break, where matter continues to exist even though we cannot see it. Darkness becomes not a threat but a teacher, showing us that visibility is not the same as existence, that things can persist and matter, even when they are hidden from view. The universe contains both light and shadow in balance. For every star that shines, there are vast regions of empty space where no light reaches. For every galaxy glowing with billions of suns, there are dark matter halos that contain even more mass but remain invisible. Balance is not uniformity. It is the coexistence of opposites, each giving meaning to the other. Light is meaningful because darkness exists. Stars are remarkable because most of space is empty. Black holes and the light they bend around themselves are two parts of a larger whole. This balance extends to time as well. Black holes slow time near their horizons while the rest of the universe races ahead. They create pockets where duration stretches, contrasting with the rapid flow of time elsewhere. This interplay between fast and slow, between the hurried and the patient, reflects a deeper principle. The universe accommodates all paces, all rhythms, all rates of change. Nothing is universal, everything is local. And in that locality, there is room for every kind of experience. Finding peace in cosmic darkness means accepting that not everything needs to be illuminated. Some things exist beyond the reach of light, and that is acceptable. Some questions remain unanswered, some processes remain hidden, some truths remain inaccessible, and the universe continues regardless. Our inability to see everything does not make the unseen less real or less important. It simply marks the boundaries of our current perspective. Black holes, in their patient darkness, offer a model for acceptance. They do not struggle against their nature. They do not resist the gravity that defines them. They simply are what they are, existing in equilibrium with the laws that govern them. There is no conflict, no inner turmoil, just the calm persistence of an object being true to its own physics. In this, they embody a kind of peace that comes from alignment with fundamental reality. As you drift towards sleep, let the image of a black hole settle in your mind, not as something to fear, but as something to learn from. Let its darkness be comfort rather than threat. Let its patience remind you that time is not your enemy. Let its transformation show you that endings are not final. Let its balance with the light around it teach you that opposites can coexist in harmony. Darkness as teacher has been waiting through cosmic time to share this lesson, and tonight, in the quiet of your rest, perhaps you can receive it. The universe holds all things, light and dark, fast and slow, known and unknown, in a balance that requires no effort and allows no failure. You're held in that same balance, safe and whole, part of the pattern that includes black holes and stars and everything between. Rest now in that knowledge. Darkness written in stars has always been part of the story, and tonight it is part of yours. As we drift toward the end of this quiet journey, let yourself rest in the knowledge that black holes are not threats, but teachers. They show us that the universe contains darkness and light in balance, that endings are transformations, and that time itself is softer and more flexible than we imagine. Even now, as you lie still, black holes across the cosmos continue their patient work, shaping galaxies, bending light and holding the memory of stars long gone. You are safe here, far from their gravity, free to imagine vastness without fear. Let your thoughts settle like dust in the quiet dark. Let the weight of the day ease away, replaced by the calm of cosmic perspective. Black holes remind us that the universe is vast enough to hold all things, gentle enough to transform what seems lost, and patient enough to wait for understanding to arrive in its own time. Close your eyes now. Let the darkness be comfort rather than threat. Sleep well, held by the same gravity that shapes stars, the same time that flows through everything. Good night.